once I had this LED lantern, it's not bad actually. This is not that one broke. It goes this cold white light, it charges from the wall, it has the battery inside. So once it broke, and first I thought to trash it because it was dirt cheap, it wasn't worth repairing at all, but then I took it apart to check if I can fix it quickly, and I saw that the components inside are cheap, nothing spectacular, but the enclosure itself, it's really well made and well suitable for the modification, and I decided to make a project to modify it, to insert the colorful LEDs and to insert microcontroller and to PWM control these LEDs. This is the original lantern as it comes from the shop. This is the modified one. We have these colorful piranha LEDs here, and the original one has cold white light. And the modified one has several modes. And this one, for example, is the flame imitation. Camera conceals it a little bit, but we see this kind of dancing pulsations from side to side. Now let's look how it looks inside and why it is so good for the modification project. What do we have here? This is the sealed lead acid battery, 2 amp hours capacity. Then we have this PCB with a knob, the brightness adjustment knob. These are 4 LED strips connected here. They are just connected in parallel. We disconnect it. This is the PCB. Here we have this this is the wall plug connector. We have to remove it as well. And the lamp itself charges from the wall. It works fine several hours. And this is the power board. We have LED indicator charging, and inside we have LED strips, 4 LED strips. And one of the interesting things I didn't find out from the beginning is that you can remove this top cover by rotating, and then you remove it. And inside we have plenty of space wasted, and we're gonna use this space to place our custom board with the STM32 microcontroller. It will fit perfectly here. These are the original components on the right, and these my custom-made components on the left. I will insert instead. So these are the original PCBs. I have PCBs of the same size, and all the components are in the same positions. And we have the extra board with the microcontroller which will drive the LEDs. And the LED strips, instead of the cold white ones, I have this colorful piranha LEDs, and the lithium battery 5 amp hours versus the original 2 amp hour capacity one. These are the PCBs I ordered for this project. These are 4 LED strips. This is the power board. This is the knob adjustment board. This is the main board with the microcontroller and the MOSFETs. And component-wise, everything was pretty straightforward, but there were a few catches. Well, yeah, piranha LEDs colorful. I have 4 colors, red, yellow, green and blue. And I had a problem with the lithium battery charge controller, because I tried a few chips. They gave either a too small current or they overheat overheat it. And finally this thing worked for me, TP4056. You can order one on AliExpress or big retailers. It's advertised to provide 1 amp charging current. It heats like crazy, but if you make a kind of a heatsink or ground plane to dissipate the heat, it actually works pretty decent. If not 1 amp, at least it provides 0.8 amps without kind of significant overheat. And another tricky thing is this charge indicator LED. It's the common anode LED. Because most of them are common cathode, and common anode is hard to find. And I ordered some on AliExpress. They sent me different ones, but these are RGB with a common anode. So I just stripped off 1 pin and it worked for me. A bit dirty, but it works. Everything else is pretty standard and straightforward, like the tactile button, the double shot key, resistors, capacitors, connectors, like Molex or JST, how they call it. I ordered the wires because I didn't want to crimp them myself. What else? I have the fuse just in case, because it's the lithium battery, it's dangerous stuff, just extra protection. These are MOSFETs, crystal oscillator, STM32 chip. Everything else pretty straightforward. You can get it from any big retailer. So yeah, I didn't film the soldering. Didn't have time for that. This is the first check if it works. So we have the board connected via ST-Link, and we want to check if the chip responds over the wire. So we power it on, and we run ST-Link utility and press connect button. And perfect. The chip is alive, it responds, and then we check option BIOS to make sure the readout protection is disabled, otherwise it won't allow us to program the chip over the wire. And now we have to program it. I'm running Visual Studio, I just run my project and it flashes the microcontroller immediately. And now it flashed, and in theory it should work. So this is the first check, it's flashed, I connect a single LED strip and it should light up if everything's fine. Perfect, perfect. So it lights up. I can change the modes, and now we'll assemble the whole thing to check if it works, but yet without the enclosure. So everything's connected, we see that all the LEDs working, buttons work, the knobs work. I can adjust the speed with the knob here, for example. The button changes the modes. Oh, sorry, where is it? It's on the other PCB. So this is the another mode. I had a couple of problems with the badly soldered pins on the STM32 chip, so I had to resolder them, and it was fine. Now we can assemble the whole thing into the enclosure. Let's try to assemble the whole thing. We made sure that it works. We have the enclosure disassembled. We removed the original parts. So I inserted my LED strips. A bit dirty way, I just soldered the plastic. So let's put the wires inside to make it neat. Then we just connect to these two things, should fit together. And now this thing, we can insert it into the cup. It just slides in. Now what next? Now we have to pass this wire. On the top we'll have our main control board with the STM32 chip. This is its power and few other signals. We have to catch it from the bottom. Here is it. Perfect. Now, what next? First, is this PCB the power board? It slides in here. You have to apply some force here, but looks like I made it pretty decent with the sizes, because it's not wobbly, but it's not too tight. I just had to apply a bit more force here. So now we have this PCB in place. Now, where we have this knob board, it goes here some way. We have to find the right position. It slides into its socket. Perfect. I found it. It's in place. So we got it. Now what next? Now we want to connect the LED strips, and we have to make this in order, because I have them numbered like 1, 2, 3, 4. So I'm connected them in order. This is number 1. It goes here. This is number 2. Number 3 and 4. Perfect. Now let's push the wires inside to close the top lid. Now I'll just close the top lid. Later I'll insert some spacer here to prevent the PCB from wobbling. Perfect. Got it. Now, what next? We'll connect the wire from the main board. This one from the knob board goes here. Now let's check that it still works. And the knob, it goes here. Perfect. Connecting the battery. Let's check. Perfect, it works. Now, I don't yet have the button cap, so I'm using a screwdriver to push the button to change the modes. And here we see that all the LEDs is working. Everything's fine. Now I want to secure the battery into the enclosure. This is another cheap and dirty but working solution. I have this piece of rubber from the bicycle tire, and I'll use it to kind of support the battery and to prevent it from wobbling. Because I don't want it to wobble inside. And since this battery is way smaller than the original one, there's plenty of space left, and it will wobble if you don't fix it inside the enclosure. Let's push it a bit deeper, because it may prevent the bottom lid from closing. Perfect. Now let's connect the main board again and the knob board, and looks we done here. Looks neat, doesn't wobble. Checking once again, it works. And finally we can screw the bottom cover. Just need to find the right side, because it's not symmetric. Perfect, it fits. it's ready. Now I'll tell a bit about the firmware, the code I wrote for it. So here is ST-Link interface connected to the microcontroller via SWD or single wire debug. And I'm using Visual GDB, it's the plugin for the Visual Studio. It's commercial, but it's really great. I like it because I'm used to work with the Visual Studio. There are a bunch of settings, and I can use either STM32Cube modern library, but I looked at it several years ago. I didn't like it at all because I'm using this older STM32 STD peripheral library. They called it the legacy library. I'll tell a bit later about this. So we have various settings like which particular STM32 chip you work with, and why I'm using this older legacy library, because it's just more straightforward, because if you take any standard function and dive into it, you immediately see what happens on the register level, on the low level. In STM-Cube, I remember, you had to dive 10 times into nested functions to get down to the actual registers and the low level. And this is kind of a thin and convenient level of abstraction. So from the one side, you don't work with the registers, but on the from the other side, if you want to look under the hood, you can do this quickly. So, and then what? We have the code. We press run, I turn on the device, and as I run the project, it flashes the microcontroller immediately, and it works. And now I can debug it, I can add breakpoints. For example, here I'm measuring voltage. So I added breakpoint, I see VDD, it's the supply voltage for the microcontroller. And I have 2.4 volts here. It's measured in millivolts, by the way. What else? We have VCC, this is the battery voltage, but we have 4.5 because we are on the USB power right now. And we can debug it just like the normal PC application. A little bit about the project. I have this config.h file with the settings. So I have PW M cycle 8000 CPU ticks long, and having 72 MHz the CPU core clock frequency, we have the PWM frequency 72 millions divided by 8000, so around 8000, or around 9 kHz the PWM frequency or the flickering. It's a lot, you won't see it with an eye, but if you lower it down to around 1 kHz, you can see the wires whistling. But on 9 kHz it's not, no whistling at all. And I have a C-stick interrupt around 100 times per second. It recalculates all the brightness levels for all the LEDs. And the interesting thing I stumbled upon while writing this code is that first I wrote all the logic using floating points numbers, because in BlueARP I use more powerful microcontroller STM32F4 and it deals with floats perfectly. But this one, it doesn't have coprocessor, so it emulates float math and it's painfully slow. As you remember, maybe 3086 machines, if they didn't have coprocessor, they were really slow calculating math. And yeah, I wrote the code and I thought, why it's so painfully slow? It barely could calculate 8 times per second, this interrupt. And then, as I found out that it doesn't support float numbers, float math natively, I rewrote all the code using integers, and then it became much faster. There are a few catches here as well, so you want to make sure you don't have overflow of the 32-bit numbers, because 64-bit numbers, they are supported by, they will be slower as well as 32-bit integers. So yeah, you can have only integer numbers, and if you want to multiply by 0.8, you first divide by 8 and then divide by 10. But apart from that, the math is pretty simple. So how it works, for each LED I have kind of piecewise linear function. I define the next brightness level and the time interval to reach that brightness linearly. So I tried to paint how it works for the flame imitation, for example. I have this piecewise linear function. I have two ranges, like top and bottom brightness levels, and piecewise linear function that always goes from top to bottom brightness, up and down. And here and there we have we pick up brightness randomly within this interval. So the pulsations are randomly either a bit slower or a bit higher, and we have this time interval with the random element as well, either a bit shorter or a bit longer randomly. So we always have these pulsations, but they randomly change kind of the amplitude and the speed, and so it looks quite good. So here's the schematic, the microcontroller in the middle, the minimum surroundings like the capacitors, the oscillator. We have a couple of analog inputs, this one for measuring the supply voltage with the protective Schottky diode. And here we have rows of MOSFETs which will drive the LEDs, with the pull-down resistors to make them closed by default. And these go to LED strips. And here is the PCB, the traced PCB. We can check it in 3D. Looks pretty decent. And this is the schematic of the power board. The lithium charge controller, the double Schottky to prevent the current floating from the battery to the charger and vice versa. Here we have a linear regulator for the microcontroller, and here I made a mistake first, because first I used the linear regulator I had, but it had a huge voltage drop, like 1.1 volts. And since the lithium battery discharges, it discharges like down to 3 volts, and on the output of this regulator we have 3 minus 1.1, like 1.9, and below 2 volts this microcontroller just shuts down, because 2 volts is the minimum allowed supply voltage for it. So I had to replace this with another linear regulator with smaller voltage drop. And here we have this plane to dissipate the heat from the IC, from the lithium charge controller. And here we have the linear regulator. As I found out, I can't go without it, because first I thought lithium has like 3.6 volts, maybe I'll just power a microcontroller directly from the lithium battery. It works, but the problem is that fully charged lithium battery delivers around 4 volts, and this voltage is too high for debugging, so you can't debug it. The microcontroller itself didn't burn, it has some, I think, extra. So yeah, it's better to use this linear regulator for microcontroller voltage supply. Ideally, I would better have like 2 or 2.2 volts regulator. I didn't find I had only 2.5, but it's still fine, because if the voltage drops, you can measure the supply voltage with the microcontroller itself, and since it goes below some threshold, you kind of can initiate the power down sequence or something like that. So this is the power board in 3D. The button model is from the BlueARP. It's not from here, but doesn't matter. Forgot to add for the PCB design, I'm using KiCad application. It's free and it's great. It has a huge library. It's only rarely I had to make my custom footprint or schematic element. And now it got dark. Let's check how it works in the darkness. So this is the first mode. It's the flame imitation. Pulsations, and each LED strip kind of pulsates independently from others, so it can dance from side to side and looks pretty much like a flame. This is the same, but faster pulsations. This is a straight white light. The camera made it a bit purple, but it's actually white. The same just on the one side. This is, we can change the color with a knob. So it goes from red through yellow, and then transitions to green, and then to blue. Just a fixed color. This is another interesting mode. A bit like the previous one, but each LED strip has the independent change of color. It jumps like up and down, but the intervals are random, so they can desynchronize, and the colors play from side to side. We can make it a bit faster. The knob adjusts speed here, or slower. This one I got kaleidoscope. Each LED changes the color randomly. Again, it's piecewise linear function, but the next point and the interval is chosen randomly. And here it's not drastically changing colors. It may be white or mix of colors. But by the way, this looks like some garlands, LED garlands work. I can adjust the speed with a knob here. The speed of these piecewise linear functions change. I call this one fireworks. So they flash and then they keep flashing through the random intervals. Actually, constant intervals with a bit of randomness. So over time, then they will desynchronize more and more. And finally, they will like blink randomly. We can speed it up. They will desync. And this is, by the way, looks like club illumination. Algorithm-wise, each LED blinks at random intervals, or kind of constant intervals with a small random addition. So yeah, they blink together and then they desync over time. These are just to add something else. I made this kind of, it blinks in cycle over and over, repeating the same program. This is another blinking pattern. it goes like up the spiral. But yeah, the most thing I made it, because I made it, is this flame imitation, the main mode. I wanted to get this kind of warm, pulsating glow to check how it will work. Maybe a bit better to see when couple of them, how it kind of pulsates. Yeah, before Christmas is just a perfect thing. So, this is how it came out. Thanks for watching. In the description I'll leave the links to the project files, Visual Studio, KiCad, PCB design, all this stuff. If someone's interested, you can still order. Yeah, I'm not sure about the abroad, if you can order, but I think, yeah, you can. So, yeah, if you have any questions, write down in the comments, I'll try to help. Thanks for watching, bye.